Okay, so we're going to give a brief intro to parallel computing and just give you some general tips for writing code that runs relatively efficiently. So I'll talk about what that means. Okay, so just some preliminary pointers for you. So when we say parallelization, what I mean by that is distributing a large or a long-running computing task so that we make use of multiple processing cores, or so you could have processing cores on the same computer. As you know, many even most of the laptops we use now have multi-core, maybe four cores, 8 cores, right? So that allows us to parallelize even within our own working whatever laptops or workstations that we're on. Or more generally, if we use a computing cluster, we can even distribute jobs over multiple or different machines as long as they can talk to one another. Okay, so that's what I mean by parallelization. Some things, of course, parallelize well, better than others. So we're going to talk a little bit about what use cases these include. So that's a key question we want to talk about today. So if for tasks that can parallelize well, then we can greatly reduce the runtime. So if it takes 10 hours, if we were to run it on one thread, on one CPU thread, in of course the best case, if it would divide by n, where n is the number of CPUs we use. For most practical scenarios, it won't exactly be divided by n, because there's often going to be some overhead associated with parallelizing. So if we can get a speed up that's close to a factor of the number of cores we're using, then that's a good result. Okay, so I'll give you some examples of that today. Now, before going into the actual parallelization part, I want to mention that we should first write code that is functional, that works, and that we've made a reasonable effort to have it be efficient. Okay, because sometimes we make some common, not errors in the sense that the code doesn't work. Like, it works, but it could be doing things in an inefficient way. So I'll give you a few examples of that before we go into parallelization. So I'll do the demos in R, but the same principles could be applied if you use, for example, Python or other packages that also, so the points I'm making, for example, memory allocation would be relevant no matter what platform we're using. Okay, so some general principles first. Okay, so I noticed that there's probably more, but these are just 3 common ways that when we put together code quickly, we might make these errors such that the code might be inefficient to begin with. So let me describe what we mean by this. Okay, so first point here is poor memory allocation. So this is, for example, growing the size of a vector or a list when there's really no need to. Okay, so this can slow things down considerably. Second point here is we may make calculations in our loop, for instance, that are actually redundant. So we might be mistakenly calculating the same thing over and over, but we could simply calculate it once and then reuse that value. So that's what I call redundant calculations. And the third point is simply how we write functions. Okay, so the idea of writing functions is that we can pass variables in, and then we can use those variables throughout, which can help reduce the amount of development time, especially when we are transitioning from one use case to another. Okay, and I'm going to show you an example of that as well. Okay, so these are the 3 points I want to start with before I go into parallelization itself. So I'm going to go over here to R, and let's talk through this. Okay, so hopefully this is large enough for you to read. Is that okay? You can see large enough to read the text. Okay, good. So let's look at these functions that I've defined here. Okay, so yeah, I have 3 of them. Okay, so methods, each of them take a single number n as input, and then n basically here just controls the size of this vector. Okay, so in this first example, I create an empty vector. Okay, so that's standard syntax in R to create an empty vector. And so at each iteration, I'm going to append the value, the square, right, of I, right, to the vector. Okay, and then it just outputs the finished vector at the end. Okay, so you'll notice that method 2 and method 3 here do exactly the same thing, but they're just written slightly different. Okay, so the key here is to distinguish between 1 and 2. Okay, so what's the difference between 1 and 2? Well, here, instead of starting with the empty vector, I allocate the size of the vector that I want. Okay, so n, so I'm going to just make a vector of NAs with that length. And then otherwise, I'm going to just do the same thing, go through and then fill each element with the square. Okay, so key point here is that this second method is going to be faster. Okay, so let's see by how much it's actually faster. But before I do that, I also want to mention that in R, especially write code in R, we want to make use of vectorization, which I think many of you would be familiar with, is that we can do these operations directly on a vector in R. So if I do 1 to n, so create that vector and then simply square it, and R will use its built-in, many of these things are actually computed in C++ internally in R. So this will be handled quite nicely using R's vectorization. Okay, so we understand that these 3 functions do exactly the same thing, should give you the same output. Okay, so let's just verify that. Okay, so if I do method 1, let's just illustrate up to 10. So it'll give you all the squares and numbers from 1 to 10. And likewise for the other 2. Okay, so they all do the same thing. So now it just remains is to test the relative speeds. Okay, so of course, this is most relevant. We put in a fairly large number for n. So I'm going to put 10 to the 5 as the length of this vector. Okay, so if you haven't seen this library, it's quite useful. It's called micro benchmark. So it allows you to repeat these commands a given number of times, and it'll benchmark it for us, and it'll summarize the results quite neatly in the table. So I'm going to do that. I'll pull it up. So here I'm going to run each of these 10 times just to give it some stability, and then use the same value of n in each. Okay, so 10 to the 5th. All right, so we're going to go ahead and do that. So it'll take a little bit of time. So as you might expect, method 3 is going to be the fastest because it uses the built-in vectorization. But I want you to pay attention to just the difference that we'll see between method 1 and 2. So the only difference, as you see, as I talked about here, is this one pre-allocates the vector and simply fills in the elements, compared to this one, which appends, so basically it grows the vector each time. Okay, so it's okay. So let it go for a bit. So of course you could see how this varies as a function of the size of the vector. So evidently, if we were to use a smaller vector, the differences might be less noticeable. Okay. So that's the first example on memory allocation. Okay, so pre-allocate, it will speed things up. Okay, we're still waiting for the result. Okay, but I think it'll be quite okay. There it is. Okay, so let's pay attention to let's just look at the mean time for each method. Okay, so this is like more than 1,000 times slower, right? You see, appending the vector is highly inadvisable unless we're dealing with a very short vector. Okay, so this is 10 to the 5. So you can see that appending the vector starts to get slower and slower as the vector gets longer. Okay, so you can see is a very, very noticeable difference. Okay, so method 1 and 2, the only difference is the allocating beforehand. Okay, so a common application is if you were to do, for example, if you're doing MCMC, you should pre-allocate all the rows of your for all the iterations, right? For your MCMC, and then simply fill in each row as you're going along. So don't append new rows to your MCMC matrix. Okay, so that's one application for many of you guys. Okay, so second contrast is between method 2 and 3. So because R has nice vectorization, so it's much faster again to operate on the vector elements rather than to use a for loop to loop through the vector. Okay, so that I think we know based on working with R, try to avoid for loops in pure R if possible. Okay, so that gives you another 10-fold difference, right? So it's about 10 times faster to use the vectorization. Okay, so that's the first demo. Any questions or comments? Okay, so so second point was redundant calculations. Okay, so I'll give you an example of that next. Okay, so again, I have two methods for comparison. Again, I'm going to let n here be the size of my matrix. Okay, so in both cases, what am I doing? I am filling up a random matrix of a matrix of random normals. Okay, so it's going to be an n by n matrix and I'm going to fill it in with variables with random normals, mean 1, standard deviation 1. Okay, and so what's different is how I do this operation. Okay, so if you look at this first method, okay, so what am I doing? I'm going through the columns of this matrix. Okay, so so I have x comma I. I'm looping through the columns of this matrix. I'm taking the value of the column, I'm adding I, so I'm adding the number of the column, and then I'm subtracting the mean of I'm subtracting the mean. Actually, just for illustration, I wanted to make the columns different, but I don't think that's relevant here. So I'm just gonna do this. Okay, so I'm just gonna take just to make the point clear, and so I'm not changing things. I'm going to take the column of each. Well, actually, I should. Okay, I'm going to make this a little clearer. I'm going to define another. I'm going to do this first, so I don't mess this up. Okay, so I'm going to copy this. I'm going to do this. Okay, so I'm going to make another copy of it. Okay. Okay, so let's do this. Otherwise, I'm changing the matrix as I'm going, so that doesn't. Okay, so what am I doing is I'm, of course, it's just very much a toy example. I'm going to take, I'm going to fill in the matrix Y. I'm going to take the X and then subtract the mean of the entire matrix. Okay, and in this second method, I'm doing the same thing, except instead of writing mean x inside the for loop, I'm going to calculate, since I'm not changing the matrix x. Okay, so that's why I needed to modify this, so I make the point clear. Okay, so I'm not changing the matrix x as I'm inside this for loop. Okay, so So in other words, this mean of x is the same value each time going through this for loop. Okay, so it doesn't seem particularly onerous, right, to compute this mean function. Okay, but we would definitely save some time by just calculating it once and then using the value of x bar throughout the rest of the computation. Okay, so that's the point that I'm trying to make here. Okay, so in this second case, it's doing the same calculation, except I'm taking, I'm going to calculate the mean of the matrix, and then I'm going to do this operation using this value that I saved here inside x bar, and then putting that value in here and directly in the for loop, so I don't have to call the mean function every time. Okay, so that's the key difference that I'm trying to illustrate here. Okay, so obviously, method 2 is going to be faster, okay, again, because it's only calculating mean of x once. Here, I'm calculating mean of x n times. Okay, so these small differences like this can also add up. Okay, so again, let's use our benchmarking to see how this performs. Okay, so let's do that. Okay, so okay, I'm going to try with a few different values. So let's start with the smaller matrix. Okay, so clearly with the smaller matrix, it's not going to make as much of a difference. Okay, although you can already see there's about 2.7 times difference because of the extra calls to the mean function. Okay, so about 2.7 milliseconds versus 1 millisecond. Okay, try with a larger value. Okay, so you see the difference becomes more apparent, right? And why does it make sense? Well, because now I'm calling mean 500 times compared to calling mean just once. Okay, so you can see the gap starts to become larger. Okay, so about 0.2 seconds versus 0.015. Okay, so more than a 10 times difference. Okay, so of course, this is just a very much a contrived example to illustrate what happens when some calculations can only need to be done once, but we do them they're especially costly, right? Things that we put inside a for loop because they're going to be calculated every iteration. So the thing to ask ourselves when we're writing such code or when writing a loop is, does everything that is calculated in the loop actually need to be in the loop? Okay, because that could add up to a lot of redundant calculations and a lot of extra compute time. Okay, so that's just another point to be aware of when coding, especially when dealing with loops. Okay, any questions on that? Okay, so the third point on here was using functions properly. Okay, so I'm going to actually pull up something that's going to look familiar to one of you here. Okay, so here is okay, so this is a C++ function. So as many of you know, we can call C++ inside of R, especially for which is itself a nice technique to make use of, especially for the compute heavy calculations. We could do those in C++ and then wrap it in R, so that we can push off the most intense computations onto C++. Okay, so this is one attempt to do that. So this is a C++ function that is sourced into R, so that this can be called in R. Okay, so there's a bunch of inputs. Okay, so you have like things like so this is a protein simulation. So there's things like so this here I just want to point out. Okay, so there's the starting number in the sequence, and then also the ending number in the sequence. Okay, and so for this particular example, we know that I believe the number that gets put into here is 472 for the particular use case in the application we're doing. Now, so that's the whole point of a function argument, right? Is that if we put in this number here, then we can generalize this function to, for example, other proteins where we have different starting numbers and different ending numbers. Okay, so anything that we can put in the function definition, we should not hard code in the function itself. so that we don't have to go and change those things if we were to apply the function to a different protein or a different sequence. Okay, so I'm just going to do here a search. Okay, so what I noticed when I was going through this code is that I see that there are some numbers hard coded into this function. Okay, so I see 472 is actually typed into the function multiple times. Okay, so and then of course, okay, that's some other stuff later. Okay, so this would be an example where the function itself could be made more. Can make use of where one can make proper use of the function argument and avoid having to remember to actually go and change the function code if we were to apply this to a different protein. Okay, so that's just a tip when writing functions, make proper use of function arguments so that the code is as reusable as possible if we were to run different examples. Okay, so those are some things to be aware of, just things that I've seen commonly done by students. Just eliminating these could already make reduce a number of inefficiencies in our code. Okay, any comments before I move along? Okay, so now I want to have a little bit more of a discussion here. So here I've just listed some common types of computations that we may do in statistical computing or when we're working with data. Okay, so here are some common things that we do. We often compute likelihood functions. Okay, many of us who work with Bayesian statistics do MCMC. Okay, and often when we need to, if we're doing testing a method, we might need to do a simulation study. Okay, so when we do simulation study, we might need to do various repetitions. Okay, so before we actually go into tools for parallelization, I want us to think a bit about, well, which of these things can I actually do in parallel and under what circumstances? Okay, so let's see if you guys have any thoughts on any of these. When can we apply parallelization? So there's three kind of cases here. Some of you have encountered some of these already, so let's have you guys chip in a little bit here.
So I think the first two will be more difficult. I'm not sure if it's possible. I think they will be more difficult because they are sequential, especially computing likelihood is usually iterative and same as MCMC. But for simulation, one can definitely parallelize the simulation.
Yeah.
For example, assign them into different CPUs or different threads.
Yeah. Okay, yeah, that's right, Songjin. Very good. So you hit on one of the key points is when we think about parallelization, we need to think about what tasks actually depend on the previous iteration, right? And what tasks can be done independently of what happened in the previous iteration. Right? So MCMC is a good example of that, right? Because if you do MCMC, well, by definition, you can't run your next iteration until you have the draw for your current iteration, right? So there's an iteration dependence there, right? Which makes MCMC, at least for an individual chain, not immediately parallelizable. On the other hand, if we were to simply repeat a simulation study like 100 times or 1,000 times, and each time we generate an independent data set and then we run it through a complicated procedure, then clearly we can do those repetitions on independent processes or independent CPUs, and then we can combine them at the end. Okay, so the trickiest part, well, sometimes we can. Okay, so what is the most costly part of doing MCMC is often computing the likelihood function, right? Because if we're doing MCMC, we will need to compute the posterior. So the posterior would be likelihood times the prior. Usually the priors are quite simple, but then the computationally intensive part is to compute the likelihood, right? So that brings us to the first point here. Well, under what circumstance can we parallelize the computation of the likelihood function? Could there possibly be, say, a part within the likelihood function that we could potentially parallelize, or are we often going to be stuck with just running, calculating the likelihood just in sequence? At least I would say that in at least one of the common cases, what is the likelihood is composed of in many of our applications, right? What is the likelihood? If you were to write it down, what would it be? It would be a product, right, over all the observations in our sample. Right? So that's one of the most common setups of the likelihood function, right? We would the likelihood would be equal to the product of I from 1 to n of something, right? And that something is the likelihood of each observation. Okay, so if we think about it from that perspective, does that give us some ideas for parallelization? What might we do if the pieces are independent or in the likelihood function? Or if you were to think equivalently on the log likelihood, it'd basically be a sum of the log likelihood of each observation. Okay, so what does that suggest we can do? Well, we could parallelize inside the likelihood function and have let's say a different CPU calculate the likelihood of each observation, and then we combine them at the end, we add them up. Okay, so there are some cases where the likelihood function could be parallelized, and often we are working with independent observations. So if let's say we're working with lumber and we have 300 independent pieces, we calculate the likelihood of each piece independently and then add them up at the end. Okay, so therefore a different core or a different thread could handle the likelihood of each individual piece. Okay, so that gives some overview of when we might be able to do that. Now, what about MCMC? Sometimes we want to run parallel chains, right? So, for example, if some of you have used Stan, Stan recommends that you run parallel chains and then combine the results at the end, just to ensure that we have convergence. So, of course, those chains, different MCMC chains, can be run in parallel. Other examples of MCMC is, well, in Stan, we're running this MCMC on the same posterior in each chain, but in some techniques, we could be running MCMC on a different posterior, and then have the chains actually talk to one another to help convergence. So I'll show you an example of that at the end of today as well. Okay, so I think that covers some of the common cases where parallelization can apply. So any questions or comments before I go ahead and show you some tools for doing that? Okay, so I'll give you a brief intro to three kinds of tools we could use to accomplish do the actual parallelization. So the first one is just the do parallel package in R. So this is just a pure R-based solution. That's quite simple to use. Second is to do parallelization in the C++ code itself. So I'll give you a brief intro to OpenMP. And then the third way is a kind of an old-fashioned way. So these first two generally work or are intended for when you're running it on a single machine, and then the threads can easily communicate to each other. This third setup, sort of having a master and a slave, right? That to govern the parallelization can work on a larger cluster. So it does so what I mean by old-fashioned is that each core will write the results into a file, and then the master, who's the master node that is organizing this parallelization, will check for all the files to be written, and then direct the cores to move on to the next phase of the computation. Okay, so this doesn't require any particular changes to the code. The code is simply written as a serial code sequentially, and then but then we run the code on multiple CPUs, and then one of the CPUs is designated as the master node, and then it will take care of the parallelization and check the file system for the intermediate files that the cores write out. Okay, so 3 types of solutions. Okay, so I'm going to show you some examples. Okay, so let's go here. Okay, so the first is to use R. So this is just a pure R example. So I'm going to load up the do parallel package. So this particular workstation that I'm on right now has 8 cores. So often it's most efficient just to make use of to set the number of threads to equal the cores. Some CPUs have hyper-threading. So for example, if I go here, it'll look like that I have 16 CPUs, right? But many, especially if you're using Intel CPUs, many are hyper-threaded, right? So each core shows up as 2 CPU threads, but physical cores there's 8, not 16. Okay, so R you can have R auto detect how many cores you have, in which case R would probably plug in 16 cores, but it's not necessarily going to be faster. Okay, so here I'm just showing, for a simple illustration, I'll just manually put in 8 cores to create a parallel cluster, and then register it. Okay, so again, I'm going to compare 2 implementations. So let's just read the first one. So this is like the usual non-parallelized version. Okay, so I'm gonna take 100,000 observations. So I'm going to, okay, you can see, so I'm gonna, excuse me, 100,000 observations, right, that I'm going to create a data set for. Okay, so I'm going to create data set with an X variable, 100,000 X's, mean 2, standard deviation 1, and then I'm going to create some regression observations by generating for each value of X. I'm going to generate something from the regression model 2 plus 3X with standard deviation 1. And then I'm going to fit this regression model on these 100,000 observations. And then I'm going to take the model coefficients, 1 and 2, and then I'm going to save this into this coefficient matrix. Okay, so again, I'm applying what we talked about earlier. I'm pre-allocating this coefficient matrix right at the beginning, and I'm simply just filling in a row each time. Okay, so in the non-parallel version, let's say I want to do this. So this is like an example of the independent replications, right? So this is an example of doing like a simulation study, right? I'm going to do it capital N times. Okay, so each time I'm going to generate an independent data set with an X and Y variable, fit the regression model, and then save the coefficients. Okay, so that's what this code is doing. Okay, so this is just pure R code, making use of the LM function, and then I just wrap it. So this will do it. It'll cap N here is going to be number of repetitions. Okay, so you look at the second implementation. I'm now going to use the parallel syntax here for using this do parallel package. So instead of doing a for loop, I'm going to use the do parallels for each. Okay, so this main part is the same. You see in here is exactly the same code. Now I just need to make a few changes to save the results in the same format. Okay, so here I create a matrix and I save the coefficients. So I want to be able to replicate that. So what this does is I'm going to create a vector. Okay, so it has the same coefficients, just like up here. And then this part here, dot combine equals r bind, says at the end, I'm going to r bind all these results together. So then now you can see that at the end of this, I'm going to get the same result as this. I'm going to have a matrix with cap n rows. Each row is going to have the two fitted coefficients. Okay, so you can see these two implementations do the same thing. Okay, so let's illustrate this now. So I'm going to do let's say 100 or independent simulation repetitions for each. So cap n is going to be 100. Okay, so I'm going to run this part. And then compare. So in the ideal case, they would be about 8 times faster, right? Because I'm using 8 cores versus in the parallel version versus 1 in the sequential one. Okay, so I don't. So that's the ideal case. In the actual real world results, I get about 6 times speed up. Okay, and you'll notice that the speed up depends on how complex the for loop is. Okay, so here I made each operation in here fairly, it's non-negligible because I'm fitting a regression on 100,000 observations. Okay, so the speed up would be less apparent. For example, if I did something smaller, so if each operation inside the loop was smaller, then there's going to be more overhead associated with setting up the parallelization. Okay, so each iteration in here is going to be faster now because I'm using a smaller vector. So okay, so let's also try it with fewer fewer observations. Okay, so each iteration is faster, so there's going to be more overhead associated with the benchmark. Okay, so you see actually if you simply use 1,000 observations, there's no noticeable speed up. In fact, it might actually be slower in parallel because the operation in here is fairly short. Okay, so there's overhead, but if you're doing a large, complicated simulation study, each data set requires a substantive amount of work, then this could be a substantial difference. Okay, so let's do parallel in R. The second one is OpenMP, okay, in C++. So I'm going to use RCPP, which is the usual interface to simplest interface to utilize C++ code in R so that I can call C++ functions in R. So pull up that library. Make sure the compile flags include the OpenMP flag. So I'm going to set that flag. And then I have the C++ file here. So, and again, this is just a toy example. So this is going to take as an input a matrix, and then just to control how many threads we use, I'm going to have that here as an argument of the function. We're going to use the OpenMP set number of threads. So what I'm going to do here is create an output matrix and then do a bunch of calculations looping through the rows and the columns of the matrix. Okay, so I'm going to do this in parallel. So there's a non-trivial amount of computations. Doesn't matter the specifics here particularly, but the key difference for doing OpenMP in C++ is it's actually quite simple. We just add this pragma OMP parallel for. Okay, and so that directs the code to operate this for loop in parallel across the number of threads that we set here. Okay, so it requires including the OpenMP headers, omp.h, and then compiling with the OpenMP flag, which I indicated here. Okay, but otherwise this C++ code would run just fine without this line. Okay, so we were to run with just a single thread, then you just get rid of this line, and it's working C++ code. So generally, OpenMP requires very little modification. So if you already have C++ code that doesn't do anything that is thread unsafe, okay, so thread safety is a key thing to watch out for when doing OpenMP. Very briefly, it means that the objects that you're handling inside the parallel part, they can't have race conditions. So if you're changing the numeric matrix as you're going along, that's going to fail. Or if you're accessing the same part of memory for which, or it depends on some underlying API, which actually changes or allocates memory inside, then we might have an issue. Okay, but here this is fine because each with numeric matrix, it can simply just fill in. We're filling in different entries in this matrix, and that is fine. This code is thread safe. It won't segfault by doing this in parallel. Okay, so there are some intricacies that one might need to watch out for when using OpenMP. So if that's your situation, then you'll need to you can look more into it. Okay, so in this case, this is fine. Each thread is going to take one of these rows in the matrix and operate on that row, and then it will store the result in the corresponding entry in that matrix. And none of those operations conflict with each other, so this code is fine. And is thread safe. Okay, so let's go ahead and run that. Okay, so we need to compile. Okay, and then I need to set up a matrix as the input for this function. So okay, let's start with the smaller one first. So let's do a 1000 by 1000 matrix. Create a random matrix to put in. Okay, so I'm going to run this OpenMP code. So single threaded, and then 8 threads, 16 threads. Okay, so so you can see the difference. Okay, so let's benchmark that. Okay, so you see that with 1000 by 1000 matrix, you see about a 3 times speed up by using the full number of threads that I have available on this computer. So about 0.04 to 0.013. And actually, if I were to use 16 threads, so I were to make use of the hyperthreading, actually doesn't help here. It actually makes it slower. Okay, so you see this in this result down here, 16 threads actually a little bit slower. Okay, so let's try with the larger matrix. So in other words, this is the same idea, right? With the larger matrix, there are more elements to loop through. So each operation inside the for loop is going to take longer. So we should see more benefits to parallelization with a more substantive computation for each iteration. Okay, so I'm going to create an input matrix, and then let's benchmark that. Okay, so we see about, well, maybe we should do something even bigger. Okay, so also about a little more than 3 times. So it scales a little bit better with a larger matrix. So from 1 second to 0.29, and now we're starting to see that the hyper threading. So I've used 16 threads is actually a little bit faster now than using 8. Okay, so we can do one more. So it scales n squared. So here we're seeing, so the same similar trend holds up. So now it's a little more than 4 times faster with a 10,000 by 10,000 matrix. And also there's a bit of advantage to using 16 threads instead of 8. Okay, so that's OpenMP. Okay, so if we're putting the main loop in C++, and that can be done in parallel. For example, we're calculating a likelihood function, and we're looping through the observations in the data set from 1 to n. So that could be done in parallel if the likelihood computation for each observation in our data set is non-trivial. So this would be one way to parallelize that. Okay, last point is this kind of old-fashioned setup where we use disk input and output to store the intermediate results. Okay, so I'm going to pull up some code for a project that I previously did that makes use of this this technique. So this is a kind of a manual MCMC in parallel. Okay, so I'm going to use 16, let's say 16 processors. I'm going to do 50,000 MCMC iterations. So this is a parallel tempering implementation. So each processor is going to be doing MCMC on this posterior, but it's going to be scaled. So temperature is basically what we use to flatten the posterior. So in other words, if okay, so you can see the temperature is used down here. Okay, so what I'm doing is taking the likelihood function and I'm scaling it by the temperature. So if you're using a higher temperature, you can more easily move between modes of the posterior distribution. Okay, and so I can do this in parallel. Each CPU takes a different temperature, and the idea is that we want the CPUs to be able to communicate to each other, so they're not just chains running independently in parallel, but we want the chains to be able to exchange their location in the posterior. So if I have here two chains, and the higher temperature chain explored a region of the posterior with a high density region of the posterior, I want to be able to leverage that and give it to one of the chains that are running on a lower temperature. So in other words, I want to swap data between chains every so often. Okay, so this is the swap interval here. So I want to write out some intermediate output and then have the chains decide whether to swap positions, and so that requires me to be able to access intermediate MCMC data. Okay, so this is just a very simple way of doing it. Okay, so let's just quickly run through what's going on here. So this is just setting up the matrix of MCMC samples for a particular chain. Okay, so as we talked about, each chain has to do the MCMC sequentially, of course, because each iteration depends on the one before it. So generally, I'm going to do a usual MCMC move. So this is just basic Metropolis move with random normal proposals. So I'm going to propose a new theta. Then I'm going to evaluate the posterior at the new theta, and then calculate my acceptance probability scaled by the temperature. Okay, so this is fairly standard MCMC code in R. And then I'm going to save the result in that row in the matrix, whether if it's accepted, and if it's rejected, I stay where I am. And then I save the likelihood value as well. Okay, so this is pretty standard MCMC stuff happening within each chain. So what I want to do is I want the chains to do that for most of the iterations, but then every so often I want the chains to communicate with each other. Okay, so what I'm going to do if it's at every swap interval, so every 100 intervals, I'm going to write out. So this is going to write a file to the disk with the current value of theta, the current value of the likelihood, and then I'm going to save it in this file, which substitutes which CPU I'm using and which iteration I'm on. Okay, so it's going to save this file. Okay, so therefore each chain is going to do this. So therefore we're going to need one of the CPUs to actually be managing this process. Okay, so I'm going to let the first CPU manage this process. So that's why if the guy who is the CPU number one is going to do this stuff in here. Okay, so what is it going to do? Just give you a high level overview is what it's going to do is it's going to check for whether all the other CPUs have written those intermediate files for iteration. Okay, so it's going to wait. It's going to wait and check this every so often for whether these intermediate outputs have been written. Okay, and so when they have been written, then it's going to do this processing, and it's going to do some work to tell each CPU what to do next. Okay, so it'll do this processing, and then after it's done, it's going to write this data that every CPU is going to then read into this file. Okay, and so it's going to store all this stuff. And so once the other CPUs see that that file exists, okay, so other CPUs are going to wait for this file to be computed. When it's computed, it's going to read it in, and then it's going to continue with the next set of MCMZ iterations. Okay, so this is this doesn't require any special code. It just means running a whole bunch of chains, starting them up in parallel, and then each one runs this same code. The only thing that's different is the CPU ID. They range from 1 to 16. The first one is going to handle all of this accumulation of this intermediate data, and then prepare the data for the next set of iterations. Okay, so this makes use of reading and writing intermediate results. Okay, so it's not clean parallelization like the other two examples, but it's still, nonetheless, it can be quite useful if we want to distribute this, say, over a computing cluster that have shared disk access. So the CPUs themselves don't need to be able to share data with each other. It's only shared via the file system. Okay, and so at the end, it saves all this output. Okay, so that's an example of old-fashioned way, make use of intermediate save files, and then the different cores make use of that. Now, the last thing I should mention is, well, how you actually get this started. Well, you can use command line arguments for R. So the process ID will be read into R by making use of a command line argument. So if I were to actually, so one way to start it is, you can see, if I want to run 16 things, then I just run R on the command line, and then I just input 1 to 16 in this argument here, and then that'll get read into this variable PID, and then you'll have 16 processes, 16 independent processes, and they exchange data by writing intermediate results onto the file system. Okay, so this can be a useful technique as well, which doesn't require any special packages. It's basically manual control over the parallelization process. Okay, so that's the end of what I wanted to share with you guys. Any comments or questions? Any discussion points?
I got one question.
Yeah.
So do you know if OpenMP and do-parallel work with each other, or is it just one or the other?
Okay, yeah. So can you combine these techniques, right? Well, in theory, yes, but you would be parallelizing different parts, right, of the process, right? So for example, if you're doing, let's say, a simulation study, right? So let's say you want to do 100 repetitions, right? And then you want each repetition requires some difficult likelihood computation, which has another loop inside, right? So you could use one technique for the outer loop, and then maybe your inner loop is in C++, right? But you got to make sure that you have enough cores, right, to do that. Okay, so you could have like R controlling the parallelization over different repetitions, then you can have OpenMP controlling the parallelizing of the likelihood function over independent observations, right? So that's possible. So of course you got to think about the design that we're not trying to do the same thing, right? In R and C++, but they need to go with it. But we could set up such that they operate on different aspects, right, of the simulation design. Yeah, is that kind of the point you were curious about?
Yeah. So yeah, sometimes it's just like a bit convoluted to just like use multiple parallel, because it seems like you delegate different tasks to different CPU already, and then like you're subdelegating tasks to like threads. So Yes.
Yeah,
I
yeah.
guess
So
like,
yeah. Generally, I would not recommend mixing do parallel and OpenMP. Generally, one of them is will be sufficient. So in that case, we would ask: is it more? Where should we? Where is the most intense for loop, right? That we should where we should implement parallelization. Right? So that'd be the design question that we would ask ourselves, and then focus on getting that part parallelized.
I see. Thank you.
Mm-hmm.
I have a question.
Mm-hmm.
So for the OpenMP, if we still have to handle some thread safety issues,
Yeah.
do we got? Because that's a problem I'm at. Under the for loop, the protein example, for each particle, we have many descendants. And under the for loop part, we want to combine them together for the energy computation later.
Yeah.
So we have to handle some like RTAP objects or functions. So, and in that case, it will make any problems. So yeah, how can we deal with that?
Well, as a design issue, right? So let's say we have 10,000 things to do, right? Each one is going to be split up into, you have 10,000 particles, each one is going to have 100 descendants, right? So at the end, we're going to have like 1 million things, right? So basically what we would do is the simplest design we would allocate, right, the 1 million size matrix, right, and then have each particle then fill in 100 of them, right, based on their position, right, in the loop. So inside, the computations for each particle can be done independently, and so they should be, right? So the particles don't need to interact with each other until all of the energies have been computed. Right? So everything up to and including the energy calculation should be able to be done independently, at least within each group of particles, right? So within each of the 10,000 particles, each one, those 100 descendants will depend on each other. So that should all be done in the inside of the for loop, right? But at least in theory, we could do all those computations and then save the results and save the energies and the angles into a big matrix. And that matrix is going to be thread safe, right? Because we're going to be filling each thread will be filling in a different part of the matrix.
Okay, but the issues I'm at is like once I want to return something like a numerical vector or something under the inner for loop, you're gonna have some warnings or issues. So So I mean, like we have to purely doing anything under the for loop without any RTAP objects, or we can, or you mean just the final thing we return is just like a thread safety, something like that.
Yeah. So your final output, right, of that calculation would be a matrix of energy values and angles, right? So that could be done in a numeric matrix, right? The final output could be thread safe like this, right? The stuff in here, right? So what I don't know as far as without looking into the API stuff is, well, are you allowed to use our API stuff in here, right? Even if it's not affecting the final results. So whether the different threads can create R objects and lists and that sort of stuff in here before the final assignment of energy, right? So that's something that I don't know the answer to off the top of my head because I haven't done it in that way. But that's something you might need to test, right? To see whether you can create, whether inside this for loop you can create lists and that sort of stuff. And because the lists are not going to interact with each other. I think that's obvious, right? Like you create a list for each particle if you need to, or create some object for each particle, and whether of course, they should not interact until at the end. The only object that all the particles should write to is this shared numeric matrix, right, with the final energy and angle values. Okay, so those would be my high level tips. Of course, you may have already tried various things, but that we can discuss more in depth in a separate, maybe tomorrow, right?
Okay, sure. Thank you.
Mm-hmm.